Okay, a 95% confidence interval has a critical value, a z-star of 1.96. However, we may occasionally want to know different percents confidence intervals. And so in this case, we want 98% in the middle, which means there's 2% out in the tails of the distribution. That's 1% on the left, 1% on the right. So to look this up in Table A, you can either look for 0.01 or 0.99. Either one of those will give you the correct z-value. The first one will just be negative. So if we take a look, what we have is 1% of the distribution, and we're looking for the z-value that corresponds with. We do not have the z-score yet, so we don't go on the outside of the chart. We have the proportion. We know it's 0.01 to the left, so we're searching for the closest thing we can get, and here we get 0.0102, 0.0099. So it's in between these two numbers. This one's a little closer, so let's take that. That's negative 2.33. So the actual z-star then would be 2.33. Okay, here we have kind of a backwards situation. We know the confidence interval itself, and we want to come up with the standard deviation of the sample means. We're also given that the mean is right in the middle of these two, so it's 105. So essentially what we're doing is looking at that formula backwards. This formula right here. We know that in the middle is 105, and then we have plus or minus this term right here, this error margin, and we know that's equal to 10. How do we know that? Because the confidence interval that they gave us was 95 and 115. If 105 is right in the middle there, we're going plus or minus 10 units from this 105. So what we do is set this part right here equal to 10, and we need just this part. Now we don't know what this is exactly, and we don't know what this is exactly, but that's fine because we do know z-star. Z-star here is 1.96, or you can use 2 as a rounded figure here. So if 2 times this quantity right here gives us 10, then this thing right here must equal 5. 2 times what number gives us 10? This number has to be 5. So the standard deviation of sample means is 5. Okay, we're comparing two different confidence intervals here. The easier one to pick out is D. 90% confidence means we're 90% confident that we'll catch the population mean. 95% confidence means we're 95% confident. So which one is less likely to contain the population mean? When we're less confident. Here we're less confident that we'll actually catch it, so it's less likely to catch it. Smaller than, if you think about the confidence intervals drawn as a horizontal line, the wider the net, the longer the line, the more likely you are to catch it. So a 95% confidence interval is going to be spread apart further than a 90%. The more you spread your confidence interval out, the more likely it is that you'll catch the mean, the more confident you are that you can catch the mean. So a 90% confidence interval would be smaller than a 95, less likely to catch the mean. Okay, here we're just looking about the assumptions. We can't assume a simple random sample. That's actually very hard to get in many situations. The best we can get is something that's hopefully somewhat representative of the population. Here we can assume B. This is one of the definitions of 95% confidence intervals. And C we can also assume. Remember that the sample mean is the starting point for the confidence interval, and then you go plus or minus around that. If you look at the formula here, you're starting with the sample mean, then you're going a little bit to the left, and with the plus sign a little bit to the right. So that guarantees that the sample mean will always be inside your confidence interval. The population mean will be in there 95% of the time. And these are not, we assume them, but they're not always realistic, especially E. E is almost never true, and we'll talk about that in upcoming chapters. Here we have some interpretations of a poll. Some of the things that are wrong here is at least 19 is not correct. When we say 95 times out of 100 will be right, it's not at least 95 times. If you take 100 samples, it may turn out that 90 of them catch the population mean, that 90 of them are actually correct and 10 are wrong. On average, it will be 19 out of 20. That's 95%, but there's no guarantee that we'll have at least 19. Here, our basis for saying 95% of the intervals will catch the population mean is assuming that we're starting at the population mean. So here, we're not basing it on the specific, any one specific sample. The 19 out of 20 comes from the actual population mean. Here, again, we're 95% sure that it'll be within 3 percentage points, but that also leaves 5% chance that it's going to be outside of that, more than 3 percentage points away from our sample mean. Here, this is just a definition of p-value. Make sure that you know this part. We're assuming the null hypothesis is true, otherwise we can't draw the normal distribution to work with. So we assume that's true, and then 3% chance that we're going to get our results or something even further out into the tails. With a p-value of 0.05, or sorry, an alpha level of 0.05, you'd be looking for p-values that are less than that in order to reject the null, and both of these numbers are less than 0.05. So there's lots of critiques of the p-value. One is that we'd like to know exactly what p-value the study came up with. Instead of just some vague range, a p-value of 0.001 is a lot different than a p-value of 0.049. And also, the p-value itself is only statistical significance. It only tells us information about statistical significance. Ideally, we'd also like to know something about whether or not this finding is actually important in real life, which is called practical significance. Question 9 here asks you to create a confidence interval, and you're starting with the sample mean of 0.22 plus or minus z star, which in this case with a 95% confidence interval would be 1.96. If you want to use 2, that would be fine. And then we need the sigma over square root of n. So sigma is given to be 0.10 right here. Square root of n, the sample size is 35. So you're plugging all of those into this equation right there. And we would get this as our confidence interval.